Hello, everyone. Today, I will present Anti-I2V, safeguarding your photos from malicious image to video generation. Video diffusion models are advancing rapidly. Open-source systems like WAN, CogVideoX, and OpenZora, and closed-source models like VEO, CDance, and Kling can now generate realistic videos from text and even animate a single input image into a coherent video. This creates exciting applications, but also serious safety risks. With one image, an I2V model can animate a real person into realistic videos, making it easier to create misleading videos, impersonations, or unauthorized manipulations. To prevent such misuse, we leverage adversarial attacks as a proactive defense. Specifically, we craft imperceptible perturbations into the user's input image, disrupting I2V models and forcing them to generate degraded or identity misaligned videos. However, existing defenses are still limited. Many were built for text, image, or image-to-image diffusion, not image-to-video. Some I2V defenses depend on unit-specific designs, reference poses, or full video inputs. Others require heavy attention losses or external networks using at least 60 gigabytes of GPU memory. Most importantly, many methods perturb only RGB pixels, which can be weakened by compression, blur, denoising, or purification. This motivates a robust architecture-friendly defense for diverse I2V models. We propose Anti-I2V built on three components. First, dual space perturbation, or DSP, optimizes the protection not only in RGB pixels, but also in lab color space and the frequency domain. Second, inter-representation collapse, IRC, disrupts high-level semantics by pushing deeper features to mimic early low-information layers. Third, internal representation anchor, IRA, moves the protected image's internal features toward an unrelated anchor image, breaking identity and semantic reservation. Common perturbations in RGB mainly change raw pixel intensity, but this type of noise can be suppressed and purified. To make the perturbation more stable and robust, we first convert the image in a lab color space. The L channel controls luminance, while A and B control color directions. In DSP, we only optimize A and B channels, so the image stays visually close to the original, while the perturbation becomes less noticeable and more robust. The second part of DSP works in the frequency domain. Using the lab-protected image, we apply DCD and perturb the low-frequency coefficients in top left sections, which capture the image's most important core structure and texture. Instead of adding superficial pixel noise, Anti-I2V directly alter core, structural, and textual information used for video generation. Finally, DSP combines lab color perturbation with DCT-based frequency perturbation, producing an image that remains visually similar to the original while being more robust to adversarial purification and common transformations, and still maintaining strong disruptive effects on I2V generation. Next is inter-representation collapse, or IRC. Our layer analysis shows that early layers carry little semantic information, while deeper layers encode identity, structure, and texture. IRC disrupts this propagation inside the video denoising module. Specifically, we align features from the last three layers to the third layer using an MSE loss. Intuitively, we force deep semantic features to behave like early low-information features, weakening identity preservation and temporal coherence. IRC disrupts information flow across layers, but we also want to disrupt feature extraction inside each layer. This is the goal of internal representation anchor, or IRA. We introduce an unrelated anchor image. Then, for both VA and video denoiser, we minimize the feature distance between the protected image and this unrelated anchor image. Hence, the protected photo is no longer represented as itself. Its hidden features are pulled toward a different image, which damages identity preservation and semantic consistency. Compared with earlier defenses that mainly target the final VAE output, IRA explicitly attacks layer-wise representations inside both the VAE and the video diffusion model. Putting everything together, Anti-I2V start from a user photo. We construct a protected image using DSP and find the optimal image with IRC, IRA, and the auxiliary and diffusion objective. The result is a photo that looks similar to the original, but causes I2V models to generate distorted, identity misaligned, or temporally unstable videos. For evaluation, we use two settings. First, CVPR' text, focused on facial realism and identity consistency. We use a total of 5,000 videos. Second, UCF 101, focused on full body action and motion coherence. We evaluate 1,000 videos in total. We test on CogVideoX, 5B, DynamyCrafter, and OpenSora 1.2. The metrics include identity similarity, clip FICA for face quality, Q-align for frame and video quality, and deno similarity. In all cases, lower scores mean stronger protection. Quantitatively, Anti-I2V provides the strongest protection across datasets and architectures. On DynamyCrafter with Celevi text, it drops identity similarity from 0.528 to 0.151, and Q-align quality from 0.794 to 0.047. Similar gains appear on CogVideoX and OpenSora, with the strongest degradation in identity, face quality, video quality, and deno similarity. This shows Anti-I2V generalizes across UNet, DIT, and MMDT video generators. Now, let us look at qualitative results. With Anti-I2V, the generated videos become much less reliable. We see stronger identity degradation, visible artifacts, distorted facial features, and weaker temporal consistency.